Visual patterns in nature. Mathematics in the modern world. Have you ever wondered why bees use hexagons for honeycombs instead of other shapes? These geometric patterns are not only natural wonders but also practical solutions for our lives. As we explore today's learning objectives, keep an open mind about the patterns in our daily lives. First, we will identify geometric and visual patterns, such as those in beehives. Next, we'll examine how these patterns shape our lives. Consider how recognizing these patterns could impact your daily life or studies. Let's explore these concepts together. Mathematics provides a unique perspective on understanding the world, often described as nature's language. Patterns observed in nature reflect mathematical rules found in numbers and shapes. Recognizing these patterns offers insights into the natural world, revealing its beauty and complexity. There are 5 geometric and visual patterns in nature. Let's start with symmetry. Symmetry is an intriguing concept characterized by balanced repetitions in objects or designs. A shape has symmetry if it can be reflected, rotated, or repeated while maintaining its structure. We will explore different types of symmetry and their applications in both natural and man-made objects. Types of symmetry. Reflectional symmetry, or bilateral symmetry, occurs when an object can be divided into 2 mirror image halves along a straight line, known as the axis of symmetry. Examples include butterfly wings, which mirror each other when divided down the center. The human face, where vertical division reveals similar left and right halves. Natural elements like orchid petals and tree leaves, often showcasing reflectional symmetry, enhancing their beauty. Rotational symmetry occurs when an object appears unchanged after specific rotations around a central point. Examples include starfish, remains the same after a 72-degree turn. Snowflake, exhibits symmetry at a 60-degree rotation. Sunflower, looks unchanged after a 10.42-degree rotation. Translational symmetry involves an object repeating itself through sliding without rotation or reflection. Examples include fish or snake scales and the stripes on zebras or tigers, both showcasing consistent patterns in nature. This symmetry is not only visually appealing but also functionally beneficial. Glide reflection symmetry combines translation and reflection, shifting and mirroring an object simultaneously. Examples include human or animal footprints, which repeat and mirror each step, and the skeletal structure of sea pens, as well as the branches of guavas and the fronds of ferns. These illustrations show that glide reflection symmetry is a vibrant aspect of the natural world, beyond just a mathematical concept. Nature favors symmetry for several reasons. Biological efficiency. Symmetry allows DNA to code structures once and repeat, simplifying growth and development. Locomotion. It provides balance, enabling efficient movement in animals and reducing challenges like walking with uneven legs. Structural strength. Symmetry distributes weight evenly, helping organisms like sea anemones and trees withstand environmental forces. These factors are vital for survival and efficiency in various habitats. Humans utilize the power of symmetry in various aspects of daily life, such as architectural facades and logos, which enhance visual appeal and memorability. The construction of domes and circular plazas, ensuring stability and beauty. Tiled floors and wallpapers, creating harmonious patterns that add elegance. Symmetry is both a natural phenomenon and a tool that enhances our environment. The next visual pattern is the spiral, a captivating geometric pattern found in nature and design, defined by a self-repeating curve that expands or contracts around a central point. Key features include a central origin, a continuous curve, regular spacing, and a self-repeating structure, contributing to the beauty of spirals. Next, we will explore various types of spirals in nature and human creations. The Archimedean spiral is a notable pattern in nature and design, characterized by equal spacing between turns. This spiral can be seen in nature, such as in fern fronds, orb weaver spider webs, and even fingerprints. Recognizing these patterns enhances our appreciation of nature and inspires creativity in art and architecture. Logarithmic, equiangular, spiral, where each turn expands exponentially outward. Examples include the nautilus shell, falcon diving paths, and tropical cyclone winds, all showcasing nature's use of this spiral for balance and beauty. Fermat's spiral is a captivating natural pattern featuring two symmetrical spirals branching from the center. Examples include sunflower seed arrangement for efficient packing and visual appeal, pinecone scales optimizing seed dispersion, daisy center pattern showcasing symmetry. Next, we'll examine why nature utilizes spirals. Nature's use of spirals is fascinating and serves essential functions for efficiency and growth. Key reasons for their prevalence include space efficiency. Spirals help plants arrange seeds and leaves at optimal angles, maximizing growth and resource allocation. Proportional scaling. Animals with shells grow by adding chambers along a spiral, maintaining shape and balance without needing to adjust as they age. Resource and energy maximization. Spirals enable efficient interaction with the environment, aiding in processes like sunlight and water collection for plants and aerodynamic efficiency for predators. Understanding these patterns inspires human innovations, which will be explored further. The spiral's versatility is evident across various fields. In data storage, CDs and DVDs utilize spiral tracks for efficient data access. In transportation, helical gears enhance power transfer. Additionally, spirals inspire creativity in consumer goods, arts, and designs, such as spiral staircases, showcasing nature's influence on human innovation. Another visual pattern is fractals, which uniquely blends art and science, featuring self-repeating patterns on various scales that create complexity and beauty. Examples include Romanesco broccoli, where each bud mirrors the larger structure. River networks, illustrating self-similarity in branching. Tree trunks, with branches dividing in efficient, beautiful patterns. Understanding fractals offers insights into natural and man-made systems, revealing how complex patterns emerge from simple rules. Fractals are essential in nature for three key reasons: infinite surface, finite volume. Fractals maximize surface area for efficient gas and nutrient exchange, crucial for sustaining life. Genetic code efficiency. Recursive patterns in fractals mirror how DNA guides plant growth, allowing complex structures to form with minimal instructions. Maximizing resource capture. Fractal patterns in leaves and roots optimize sunlight exposure and soil contact, enhancing plant survival in diverse environments. Recognizing these fractal applications deepens our appreciation of nature's efficiency. Next, we'll discuss human adoption of fractals in various fields. Today, we explore how humans utilize fractals across various fields. Telecommunications. Fractals design compact, efficient antennas that operate on multiple frequencies, enhancing modern communication devices. Computer graphics. Fractals create realistic landscapes and textures, allowing for detailed simulations of nature in movies and video games. Healthcare. Fractal analysis aids in diagnosing conditions by examining complex biological patterns in medical images. These applications highlight the transformative potential of fractals in technology and improving the quality of life. The fourth type of visual pattern is tessellation, an intriguing arrangement of repeating shapes that fit perfectly on a flat surface without gaps or overlaps. There are three main types: regular tessellations, single shape like squares or triangles; semi-regular tessellations, two or more shapes; irregular tessellations, varied shapes and angles. Understanding tessellations enhances our appreciation of designs in art, architecture, and nature, showcasing the beauty of mathematics and geometry in our surroundings. Regular tessellations feature a single repeating polygon that seamlessly covers a flat surface without gaps, creating a uniform pattern. Examples include honeycomb structures, where hexagons fit perfectly. Anini Y basalt columns in the Philippines, showcasing interlocking hexagonal formations. These patterns appear in both nature and man-made designs, inspiring efficiency. Semi-regular tessellations involve the seamless combination of two or more different regular polygons, creating visually appealing patterns. An example is the Fritillaria meleagris flower, which has a checkerboard design, and microscopic structures like radiolaria also showcase these patterns. This concept emphasizes the beauty of nature's designs and leads into the exploration of irregular tessellations, which are important for nature's efficiency and strength. Irregular tessellations illustrate how nature creates order from irregularity, allowing non-regular polygons to fit together without gaps. Examples include giraffe coats. Irregular patches create a camouflage pattern. Dragonfly wings. Interlocking cells form a strong, flexible pattern. Dried mud cracks. Natural tessellation occurs as mud dries and contracts. These examples highlight nature's design efficiency and problem-solving capabilities, setting the stage for a discussion on why tessellations are utilized in nature. Nature heavily relies on tessellation for three main reasons: material conservation. Tessellation maximizes area while minimizing resources, as seen in honeycombs, where bees use minimal wax for maximum storage. Structural strength. Tessellations provide excellent load distribution, exemplified by dragonfly wings that withstand wind pressure through their interlocking veins. Elimination of blind spots. Tessellations create tightly packed structures, like the hexagonal lenses in housefly eyes, ensuring a panoramic view without blind spots. These principles highlight nature's efficiency and brilliance, paving the way for human adaptations in various fields. Tessellations influence various fields, including aerospace and engineering, used for strong, lightweight structures that effectively distribute loads, critical for aircraft and spacecraft. Construction and architecture. Aesthetic yet functional designs maximize space and light, like honeycomb structures in modern buildings. Textiles and cultural arts offer diverse patterns, celebrating heritage and creativity through mosaics and quilts, allowing unique artistic expression. These applications show that tessellations are vital in shaping our environments and enriching cultures, beyond mere mathematical concepts. The last visual pattern that we will explore is the strip and wallpaper patterns, where geometry intersects with art in nature and design. Strip patterns, frieze patterns, repeat infinitely along a straight line, akin to a caterpillar's segments, enhancing architectural details and borders. Wallpaper patterns extend this idea into two dimensions, seen in natural crystals, showcasing complex, beautiful structures. Both patterns illustrate how simple geometric principles can yield intricate and captivating designs. Nature's use of strip and wallpaper patterns exemplifies the blend of form and function. Key points include directional growth. Strip patterns emerge from growth along a primary axis, balancing efficiency and flexibility. Space optimization. High symmetry wallpaper groups, like hexagonal lattices, maximize space usage with no gaps, crucial for resource-limited environments. These patterns serve practical purposes while enhancing the aesthetic beauty of the natural world, showcasing nature's efficiency and elegance. Let's focus on the human uses of strip and wallpaper patterns in nature, in three areas. In textiles and fashion design, strip patterns create dynamic apparel, while wallpaper patterns serve as a canvas for intricate designs. In architecture and interior design, strip patterns guide movement and flow, while wallpaper patterns fill spaces seamlessly, enhancing harmony. In digital user interfaces, these patterns organize information and improve user experience, with strip patterns aiding navigation and wallpaper enhancing readability. In nature, organisms combine multiple visual and geometric patterns, typically 3 to 5, showcasing complexity and beauty. Steps to decode patterns. 1. Check for symmetry. Bilateral symmetry, mirrored sides. Radial symmetry. Patterns radiate from a center. 2. Identify linear patterns. Frieze pattern. Lines repeat in a one-dimensional channel. Glide reflection symmetry, alternating lines. 3. Revisit overall shape. Consider if the form is round, spiral, hexagonal, or striped. Step 4. Analyze surface patterns. Look for tessellations, surfaces with zero gaps and overlaps. Wallpaper patterns, rows repeating infinitely across a grid. Step 5. Identify repetition and scaling, focusing on fractals, smaller parts resembling the whole. Archimedean spirals, structures winding around a central point. Logarithmic spirals, structures expanding outward exponentially. Step 6. Compare identified patterns to known types to confirm observations and uncover new insights. This process sets the stage for further exploration. Now try to identify the visual and geometric patterns of pufferfish. Remember the key points: unique body shape and inflation as a defense and geometric feature. Skin patterns with various colors for camouflage and communication. Symmetry and repetition in patterns that are both attractive and functional for survival. Nature and the universe are filled with mysteries yet to be explored. While we've gained knowledge, much remains unknown, fueling curiosity and innovation. As we investigate these enigmas, we must recognize our duty to care for our planet, as our actions today impact its future. Thank you for watching. Subscribe, like, and share. Follow me for more learning videos.